Section 3.7 is about critical points, and critical points are points on a graph where the nature of that graph changes. And let me give you an example where that happens. Let me just draw the graph of y equal x squared. We all know that that is a parabola, and we'll talk about a critical point in this graph. And if you talk about where this graph is changing, if you look at the slope of the tangent lines at this, you notice that this graph from going from left to right is decreasing in nature. It's coming down and it's decreasing. These slopes have a negative slope. They're going from top left to bottom right, which means they have a negative slope and it's decreasing. But at this point 0, 0, everything changes. And all of a sudden, when we draw the slope of the tangent lines, now this function is increasing. So the point at which it changed is a critical point. That point 0, 0, in this case, turns out to be a minimum. It's a minimum value because it's the lowest part on the graph. And because the graph went from decreasing all of a sudden to increasing, that means it's a minimum. So that is one example. A minimum, a maximum, the curve changes from increasing to decreasing. Let me draw an example like that. Maybe, well, I guess I could just draw a upside down y equals negative x squared graph, something like that. So in this case, the slope of my tangent line is right now is a positive. It's increasing. The slope of my tangent line is positive, and then all of a sudden it's 0.00 on the other side. The slope of my tangent line is now negative, and so that means the function is decreasing after that point. That would be an example of a maximum because that's the highest point on the graph at that point right there. All right, and I already gave example minimum where the curve changes from decreasing to increasing. And a point of inflection is where the change or where the graph changes its curvature, concave up to concave down. Basically, where concave up, I call it where it could hold water, and concave down if it can't hold water. A good example of that is a graph like this at 0.00. This graph changes to where it was concave down to concave up. Right here, it'd be concave up because it could hold water up inside here. This graph below here is concave down. So a point of inflection where that changes then is that at that point 0, 0. But we'll give you ways in order to find that using derivatives. And we talked about max and mins. Well, relative max and min doesn't necessarily, that has to be the absolute bottom, like the two graphs that I showed you. It doesn't have to be the absolute lowest part of the graph. We could have a graph that goes something like this. Something like that, and where we have changes in directions, we have critical points. We have a critical point here. My slope is changing from increasing to decreasing, and I have a critical point here, and I have a critical point here and here, and all those times. And these aren't necessarily maximums. They're not the highest y value in a graph because this is way higher than that guy, and they're not minimums because this point down here is way lower than that guy. But what they're called is they're relatively max and they're relatively mins. This point right here is the highest point in a specific area. This point again, here's the lowest point in a specific area as well, and so forth. So that's what a relative max and a relative min is. To find the relative maxes and mins of a graph, all we have to do is we have to find the derivative of a function and set that derivative equal to 0. And so what we find out is when the slope of the tangent lines, that's what our derivative tells us, is the slope of the tangent line. All right, when that is 0, that means our graph is changing. So when I have a horizontal tangent line, that means my graph is changing. So that's why we're setting the slope equal to 0. All right, to find the point of inflection, we're going to take the derivative of the derivative. So we're going to find the second derivative, and then we're going to find where x equals 0 on the second derivative as well. So our first example says determine the critical points of the graph f of x equals 2x cubed minus 24x plus 12. Well, critical points means we want to find the max mins and we want to find the point of inflection. To find the maximum minimums, again, we're going to find its derivative and then we're going to set it equal to 0. So let's find its derivative first. We know when we find its derivative, we're going to take the power, we're going to drop it down here, multiply by the coefficient, and then decrease the power by 1. So 2 times 3 is 6x, or decrease this power by 1, and that is 6x squared. minus 24. Again, this has a power of 1. If we bring that down, 24 times 1 is 24, so minus 24. Subtract the power by 1, and that's 0, so it's just minus 24. And again, the derivative of constant goes away. So if we want to find its maximum, we need to set this derivative equal to 0 and solve for x. 6x squared minus 24. We will add 24 to the other side. 24 equals 6x squared. Divide by 6. 4 equals x squared. So x equals plus or minus 2. And that would be where possibly a minimum and a maximum is. All right. And then to find the point of inflection, we will take the derivative of the derivative. So you can take the derivative of this guy here. So we're going to find its second derivative. We need to note that by f double prime of x. That means these two dashes here mean second derivative. All right, and again, we bring the power down, decrease it by 1, so we're going to have 12x, and we set that equal to 0. 0 equals 12x, and we solve for x, divide by 12, divide by 12. X equals 0, so we're going to have a point of inflection at x equal to 0. All right, so why I didn't go into telling you whether this was a maximum or minimum is because this next sentence down here. To tell whether it's a maximum or minimum, pick a point on either side of it and see what the slope is doing. All right. So we read the definition of a maximum minimum. A maximum point would be going from if the slope beforehand is increasing, then afterwards it's decreasing. So if we pick a point on the left side of our critical point and it's positive, and a point on the right side and it's negative, we have a maximum. And if we have a minimum, it would have to go from, here's my critical point. If we pick a point to the left and the slope is decreasing, and then on the other side, on the right side, it's increasing, then we have a minimum. So we have two critical points here, positive 2 and negative 2. So that means we have some intervals is what we call it, from negative infinity to negative 2. This graph is doing something. And then from negative 2 to positive 2, the graph is changed because it had a critical point here at negative 2, and then it has another critical point at positive 2. So in some sort, there's a change there. That's because that's what a critical point means. And then again, then it's doing the same thing then from 2 to positive infinity. So we need to see what it's doing. Let's pick a point on the left side of negative 2. So negative 3 would be on the left. It'd be smaller, right? The negative 2. And let's plug that into our derivative and figure out if we have a positive or negative slope. So if we pick negative 3 squared is 9. 9 times 6 is 54. 54 minus 24 is a positive 30. So on the left side, it's going positive. And let's pick something on the right side. Let's pick negative 1. Negative 1 squared is 1 times 6 is 6. 6 minus 24 is going to be a negative number. So our slope went from positive to negative. So that would be this graph right here, which is a maximum. So at negative 2, we have at x equal to negative 2, we have a maximum. And then if we know that now we know on the left side this is negative because we plugged, it's going negative and it's going negative 2 on the right side of here because we picked negative 1. All right, we got a negative. Now it says pick a point on the right side of, or in between here, let's pick 0. On the left side of 2, let's pick 0. So then we have 0 times 6, which is a negative. So on the left side, it's still negative. We knew that from over here, this guy. All right, and let's pick one on the right side of 2. So let's pick 3. 3 squared is 9. Times 6 is 54. Minus 24 is 30. So again, at 2, it went from a negative slope to a positive slope, and we knew that we drew this picture over here. This has to be a minimum. So then at x equal to 2, we have a minimum. And let's see, I think I pulled this graph up for you guys. Yep, if we look at this graph right here, we say that negative 2, we had a maximum, right? So the graph was coming, it was increasing, the slope of the tangent line was increasing. And then we said at negative 2, there was a change going on. These are going by 2. So at negative 2, there is a critical point, and then so it went from increasing to decreasing. And then in between here, it was decreasing is what we found. And then we have a critical point at positive 2. Again, there's a change, and now it started increasing. So that's what we found there, and we could say we could find the actual points, and all we would have to do is we would have to plug in -2 into this function to get its y value and a +2 into this function to get its y value, and we would figure out exactly where the critical points are for this graph, and it would very easily help us sketch the graph of this function. All right. So we took a look at that, and we talked about this. Maximum of the slope is increasing on the left, then decreasing on the right. We talked about that. So example 2 here says find the critical points of the graph f of x equals -2x cubed plus 3x squared minus 5. Then determine whether each point represents a max, minimum, or point of inflection. So let's find all the critical points. We take the derivative, set it equal to 0, and solve for x. So let's take the derivative of this function. So f prime of x equals, I'm going to bring my power down, decrease power by 1, so a -6x squared. I'm going to bring the power down, decrease the power by 1, so plus 6x, and then the derivative of a constant just goes away. So there's our derivative. We're going to set it equal to 0 and solve. So in order to solve this, I'm going to have to take an x out. So let's factor an x out, and we'll get -6x plus, well, actually, we could have taken a 6x out. Sorry about that. Let's factor a 6x out. And we get just left over x plus 1, or a negative, sorry, so x minus 1. And we'll solve for 0. So I took a -6x, so a negative, when I take that out, it becomes a positive x. When I take a -6 out of here, it becomes a -1. We know when these two are multiplied to each other that we have to set both of these equal to 0. So 6x equals 0, and 6 and then x minus 1 also equals 0. So we're going to have a critical point at x equal to be 0 from this guy, divide by 6, divide by 6. We're going to have a critical point from here when we add 1, so x equals 1. So we have a critical point at 0 and 1. And then to find our point of inflection, then we take the derivative of the derivative. So f double prime of x is going to equal, again, bring the power down, decrease the power by 1, which would be -12x. And then bring my power down, which is 1 plus 6. And solve for x. So set it equals 0, solve for x. So -12x plus 6. I'm going to subtract 6, subtract 6. So I have -6 equals -12x. Divide by -12, and I get x equals a positive 1/2. So at x equals positive 1/2, we have a change from concave up to concave down, or the other way around, concave down to concave up. So that's a P of I. That's what they asked us. This is a point of inflection. I say it's a POI. Now we need to determine whether these guys are maximum or minimum. So let's pick a point on the left side of 0, and then the right side of 0, and see what the graph's doing. Pick a point, let's say -1, and let's plug it into our first derivative, because that will give us the slope of the tangent line. So if I pick -1, I get -6 times 1, because it's -1 squared. So I have -6. Plus, then I have 6 times a -1, which is -6. I get -12 on the other side. So it's decreasing on the left side. And if we pick one to the right, but it can't be a critical point, so we're going to have to pick like 1/2 or something like that. So if we pick 1/2, we'll have -6 times 1/4 plus 3. So -6 times 1/4 is -6/4, which is -3/2. So -1.5 plus 3 is going to be a positive number. So on the right side of 0, it's increasing. So we know when we go from a negative, so if my slope is decreasing, to a positive, then we know we're going to have a minimum. So this guy is a minimum. And so we know on the left side of 1, we just found out here that it was increasing. So on the right side of 1, pick 2. So I have a -6 times 2 squared, which is 4. So -6 times 4 is -24. Plus 6 times 2, which is 12, is a negative. So on the right side of 1, it's decreasing. We know when it goes from a positive slope to a negative slope, then we're going to have a maximum at x equals 1. So that's a maximum. All right. One last example here. find the x and y intercepts for the graph, and this should be a review for you. We know if I just graph you a line that you guys know, just a straight line, let's say y equals negative x plus 7 or something like that. We know, what do we know about a y-intercept is we know it when we have a, sorry, whoa. When we have a y-intercept, we know when we have a y-intercept and an x-intercept, no matter what right here for my y-intercept, x is always going to equal 0. So 0 something is always going to be my y-intercept. If we're going to find an x-intercept, we know that y is equal to 0. So we're going to have something, comma, 0. So in order to find these two, if I want to find my y-intercept, let's plug in 0 everywhere we see an x, because that's what a y-intercept means. It means that x is 0. What's a y value when x is 0? Everywhere I see an x, I'm going to plug in 0. So I have y equals 2 times 0 cubed minus 5 times 0 squared plus 3 times 0. So y equals 0. I have a y-intercept at 0, 0. All right. And then so we're going to have to find our x-intercept as well. We said our x-intercept is when y equals 0. So let's set this thing equal to 0. Let's make y equal 0, and let's solve for x. Minus 5x squared plus 3x. In order to solve this, I'm going to have to take an x out. 0 equals x times, let's see, 2x squared minus 5x plus 3. And I'm going to have to factor this guy. If I factor this guy, we're going to have a 2x, and we're going to have a positive x, and we're going to have things that multiply to be a 3, and they're going to have to be the same sign. They're going to have to be negative, so it's going to have to be 2x minus 1, 2x minus 3. Is that right? If I FOIL that out, I get a 6x. No, I have to have the other way around. This should be a negative 3, and this should be a negative 1. That way it'll work out then. Yep, that way it'll work out. So that's that thing factored. If you're not sure how to factor, you can also use a quadratic equation, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's when you just plug in the coefficient. So 2 is anywhere you see an a, you're going to plug in 2. Anywhere you see a b, you're going to plug in negative 5. Anywhere you see a c, you're going to plug in 3. That'll also give you the zeros, or where x equals 0 as well. And to find my x-intercepts, last thing, we know again that we talked about this earlier, since these are all multiplications, we set all of these guys equal to 0. So x equals 0, x equal, or sorry, my bad, 0 equals 2x minus 3, and 0 equals x minus 1. And solve for x on each of these. So in this case, x is going to equal 3/2, and in this case, x is going to equal 1. So we actually have 1, 2, 3 x-intercepts. So that graph might be doing something crazy, where it's going something like this. It crosses that x-axis a couple different times. So all these things are going to help us sketch graphs out, and that's what we're going to. I hope this helps. We'll see you in class.